We are going to be working with H, a subgroup of the symmetry group of A, where A is a finite set. Let's go over what that means. Sim A is the set of permutations of A. The fact that H is a subgroup means, well, it's a subset, so we're not thinking about all of the permutations of A, just some distinguished ones. But we must include the identity permutation in our subset H. For any two elements of H, if we compose them, the result must also be an H. So this is saying that if we think about the action of F first and then the action of G combined, that will also be a permutation, and H must be closed under that operation. And in fact, H must also be closed under taking inverse. Okay, we are looking at an example. I've written A is the set of squares with each corner red or blue. More precisely, we're thinking about a particular square and all of the different ways of colouring the corners of that square, each red or blue. Because there are four corners, we're colouring each one in one of two ways. The number of elements of A is going to be 16. There are many permutations of A. We are only going to be thinking about 8 of them. That's these 8 I've described here. You'll notice that these are transformations of the plane in which our square is sitting that map the square back onto itself. And in particular, they're going to send each corner to a corner, be it a different corner or itself. So our 8 permutations in H are the identity permutation. What we get by rotating all of the squares a quarter turn or a half turn or a 3/4 turn, and then also the reflections in these 4 axes here. One way we can write these 8 permutations is in terms of just 2 of them, called R and S, where R is a quarter turn anti-clockwise rotation and S is a reflection in this particular axis. And then by combining R and S in particular ways, we can represent all of the other permutations in our subgroup. Let's just go through exactly what the correspondence is between this description and the wordy description above. So this is the identity, this is a rotation by pi on 2, this is a rotation by pi, this is a rotation by 3 pi on 2. This is a reflection in this axis. This means reflect in that axis and then do a quarter turn anti-clockwise, so that's going to be the same as reflecting every square in that axis, and then this one is the same as reflecting in that axis. Sorry, I'll make that a bit neater. And finally, R cubed S, we are reflecting in that diagonal but then doing a quarter turn clockwise, which is going to be the same as reflecting our squares in that horizontal line. Okay, let's see exactly what R is doing to all of our squares. So we can see the 16 colourings and some green arrows. Each square, each element of our set A is being mapped to exactly one square, one colouring, by a green arrow. So we can see, for example, this square has each corner coloured red. The action of R, rotating by a quarter turn anti-clockwise, or in fact any of our permutations is going to leave that square alone. It's going to send it back to itself. But if we look at this square instead, we have the top left corner only is coloured blue. If we apply a rotation, that corner is going to map to the bottom left, and we can see that if we follow the arrow, we get to the image of that square. The only other thing to say is this top right square, if we imagine rotating it, we would end up with blue corners on the top left corner and the bottom right corner, and red corners on the other two, which is this one down here. That's what these arrows are getting at. So this square is mapped to this one, and vice versa, this one is mapped up here. Let's have a look at the action of S. When we reflect in this diagonal line here, any corners on, or rather the two corners on that line are going to stay where they are. The other two are going to be flipped. In the top row, we have both of those corners that are being flipped coloured red. So actually the result is that the square, the whole colouring, is being sent back to itself. It's left alone. The same explains why that's happening in the bottom row here. Both of the corners that are being switched are coloured blue. When that's not true, when these two corners are coloured with opposite colours, switching them is going to send the square either down or up between the two rows. So we can see that these two colourings are switching, these two colourings are switching, and so on. Next, we're going to think about, for each colouring, where can it end up? Where can it be sent by one of our 8 permutations? And we get a diagram that looks like this. So we can see, for example, the top left square, which we said was always being mapped back to itself, is on its own in this subset, coloured green. We're going to call these orbits. And so we can see in this orbit, these are exactly the colourings of the square with one corner blue. If we start with any of those, we must end up at another one. So none of our permutations, be it the identity or rotation or reflection, is going to change the number of blue corners. So we must stay within this orbit. And in fact, it's also true that starting at any one of these 4 colourings, we can get to any other. And in fact, we could do that by just rotating the appropriate number of half turns. And we can see that we have an orbit here, an orbit here, an orbit here, and what this is getting at is we have the final orbit is made up of these 2 colourings, which we saw were flipped or switched between them by the permutation R, but each one was fixed, was sent back to itself by the permutation S. Alright, we have 5 orbits in this example. The goal of this video is going to be demonstrating a formula which can be used to calculate the number of orbits, which is helpful when the set A is much larger than the one I've drawn here. So in fact, we wouldn't need to draw it all out and cut our drawing into nice sections that show where the orbits are and then count them up. We can just apply our formula to find the number of orbits. Let's zoom in on this orbit here, the one with the colourings where exactly one corner is coloured blue. And we can see those 4 colourings here with a lot more detail about exactly which permutations are sending each colouring to each other. So let's see, let's start with this top left colouring. There are exactly two of our permutations which send it back to itself. We can see these are E and R squared S, where R squared S was reflection in this axis here. And that certainly makes sense. If we reflect in this axis, then we would end up with the same colouring. But we can see there are three other green arrows leading out of this colouring. We have this one with the two permutations R cubed and RS. We have this one with R and R cubed S, and finally we have this one with R squared and S. The thing to note here is that we've accounted for all of the 8 permutations in our subgroup H. We have divided them up into 4 groups of 2. So we have the 2 that fix our colouring we're thinking about in the top left, and then for every possible image of that colouring under a permutation, there are again 2 elements of our subgroup H that send our colouring to that potential image. And in fact, this reflects the general situation. So if we write H sub A for those elements of our subgroup H which fix A, where A is an element of our set A. So this was our element A. HA would be exactly this subset of H. Then we are breaking up our subgroup H into an equal, or rather into sets of equal size depending on where A is sent under that permutation. And this means that the size of our subgroup H is going to be the number of its elements that fix A multiplied by the size of our orbit. So that's the number of these colourings where it is possible for A to be mapped to. I am quite sure I didn't make that very clear, but hopefully by pausing the video and reading what I wrote earlier, that will make sense. I'm not going to prove this to you, but at the end of the video I'll give you some idea of where to look for a proof. And the key point is that this number, the size of HA, which, using this formula, is the size of H divided by the size of our orbit, is the same for each element of our orbit. So we have 2 elements of H that fix this this element of A, and also there are 2 elements of H that fix this element of A, 2 elements of H that fix this element of A, 2 elements of H that fix this element of A. And for any orbit, that number is going to be the same for every element of that orbit, because it is exactly, well, it's determined by this size of our subgroup and the size of the orbit. We are going to label each element of A by this number. So we can see we have our orbits in the full set A again, but I have written next to each colouring that number that we were just considering. So we have it is the number of elements of H that fix that colouring. So, for example, there are exactly 2 elements of H that fix this colouring, because we can have E or a reflection in the horizontal axis, which I believe was R cubed S. And for each orbit, if we add up the labels of the elements in that orbit, well, each label was the size of H divided by the size of the orbit. The number of labels that we're adding up is the size of the orbit, so altogether it's going to be the size of H. So we can see in our example, each of our 5 orbits, the elements of that orbit have labels that sum to 8, because 8 was the size of our subgroup in our example. For example, we have this orbit with 2 elements, each one labelled with 4, and of course 4 plus 4 is 8. So if we sum the labels in the whole diagram, what we end up with is the number of orbits in the diagram multiplied by the size of H. And of course in this example we have 8 plus 4 times 2 plus 4 times 2 plus 4 times 2, because there are 3 orbits with 4 elements, each labelled 2. And then we have 2 times 4, that's this orbit here, and then finally 8 is this one again, is 8 times 6, which is exactly the size of H times the number of orbits. Excuse me, I said there were 5 orbits, of course there are 6. So we have 1, 2, 3, 4, 5, and 6. All right, we have... So we are now going to count this quantity in a different way. So we are now going to go through the elements of our subgroup H and focus on which elements of A are fixed by that element H. So just to be clear, that looks like this, where we have this arrow sending a colouring back to itself. And I've said we're going to put a ring around that element. So let's just have a go at that quickly. I'm not going to go through all of them. If we start with E, well, in fact, every element of our set A is fixed by the element E. So I can put a ring around every element, and so on. We move on to R. Well, a rotation by a quarter turn anti-clockwise is going to fix this element and that element and nothing else. And then if we move on to R squared, which is a half turn rotation, that is going to fix, again, top left and bottom right, but also this top right and bottom left, and so on. And hopefully you can see that for any element of A, so for example this one here, the number of rings that are going to be put around that element is exactly the number of elements of H that fix this colouring, which is exactly the same as the label. So in this case, we're going to put a ring the first time when we're thinking about the identity permutation, and also when we are thinking about reflection in that horizontal axis, which I believe was R cubed S. So this total of all of the labels in our diagram, we can also write it as this sum over the elements of our subgroup H of fix H, where fix H is the number of rings we draw when we're thinking about that particular element, or in other words, the number of elements of A that are fixed by little h. Alright, now we have calculated the same quantity in two different ways. So we know that the sum of all the labels in our diagram is both the number of elements of our subgroup H multiplied by the number of orbits in A, and also this sum over the elements of H of the number of fixed points, the number of elements of A that are fixed by it. If we equate these and rearrange, we get an expression for the number of orbits in A. It's 1 over the size of our subgroup H multiplied by the sum over H of the number of fixed points of our element. This is going to be extremely useful. We can double check that it is true for our example, and then finally we're going to move on to another example. Let's be precise about which elements of A are fixed by each element of H in turn, and sometimes we can deal with a couple of elements of H at once because they are doing essentially the same thing. So let's start with E, our identity permutation. That fixes every point. In fact it fixes all 16 of them. So here in this page we're calculating fix of H, where H is going to be shown on the left here. And then we have R and R cubed are each a rotation by a quarter turn. So R is a quarter turn anti-clockwise, R cubed is a quarter turn clockwise. In each case, the only colourings that are fixed are those where all the corners are the same colour, which there are only two of those. So all of the corners are coloured red, or all of the corners are coloured blue. And then we had the rotation by a half turn, R squared. That fixes squares where opposite corners have the same colour. We can think of that as saying we choose a colour for the top left, we choose a colour for the top right, and then in fact the bottom right must be the same as the top left, and the bottom left must be the same as the top right. So we've made two choices. Each choice we made, we had two options, so it's 2 to the 2 or 4 colourings which are fixed by R squared, and I am going to skip over these next two, but except to say that S fixes those squares with the top row matching the bottom row, and R squared S instead fixes those squares with the left column matching the right column. Let's just fix that. Just in case the writing wasn't clear there. In either case, fix of H was equal to 4, and then finally when we have RS yes, so these are reflections along diagonals. And here we need, so for RS in particular, we need top left corner matching the bottom right corner, which means we have 3 choices of colours. And similarly for R cubed S, the top right corner matches the bottom left corner. That means we again have 3 choices. of colours. So in each case, fix of h is 2 cubed, which is 8. Okay, and now if we apply our useful formula, we find, we go through and add up fix of h. So we have 16, and then we have 2 lots of 2 because we have 2 elements of h. 1 lot of 4, we have 2 lots of 4 and 2 lots of 8. Once we've added those up, we divide by 8, which was the size of h, and we end up with 6, which is the correct number of orbits in A. Right, let's have a look at another example. This is going to be deliberately quite complicated. I just really want to convince you do not want to go through this by hand and actually find what these orbits look like. We just want to find the number of them. We can do that quite slickly using our formula. Alright, so we're going to be thinking about subgraphs of this complete graph with 6 vertices. So by that I mean we need to still have all 6 of our vertices, but for each edge in our original graph we can either include it or not. So we might include these 3 and nothing else. And in particular that's not, it's not a connected graph because this point is on its own. But we could instead have had that, and that's really not a connected graph because it's got this bit very much disconnected from that as well as that. Anyway. And then finally, H in this example is going to be permutations of vertices. So we're sending one subgraph to another subgraph by reordering the vertices, and the edges move around following the vertices. So let's see a particular example of this. We are sending vertex 1 to vertex 5, sending vertex 5 to vertex 6, sending vertex 6 to vertex 1, leaving vertices 2, 3 and 4 as where they are. That's what this notation means. I realise that's not at all clear if you haven't seen it before. So let's see where this particular permutation sends to example elements of our set A. So we have a subgraph here. When we send vertex 1 to the place of vertex 5, which is down here, send vertex 5 to the place of vertex 6, which is here, send vertex 6 to the place of vertex 1, then, for example, the edge that was between vertex 1 and vertex 5 maps to the edge between vertex 1 and vertex 5. The edge between vertex 2 and vertex 4 stays where it is because the vertices stay where they are, and the edge between vertex 2 and vertex 6 maps to this edge here. And we have another example down here. So the this sort of is a colouring. I'm tempted to call it a colouring. We're saying all 15 of the edges in this original graph are being coloured sort of black or white, and black means you can see them, I've drawn them, white means you can't. But anyway, each element of A, so this element of A, is being sent to another element of A that looks like this, and the labels on the vertices here are just for to assist with understanding. There's no, we should really remove the vertices to make it clear that all that matters here is which edges are shown, not which numbers are assigned to the vertices. All right. And now we can go through all of the possible elements of H, all the possible permutations of the vertices. We are going to calculate the number of permutations that act in the same way. I realise that's not very precise. It can be made more precise. And also the number, or rather fix h, which is the quantity we need to calculate for our formula. And this diagram here next to each class of permutations is just illustrating where the calculated value comes from. So, for example, let's start with 1, 2. So that's switching this vertex with this vertex, leaving the other vertices the same. How many permutations are there that act in the same way? By that I mean transpositions. So these are permutations of the vertices that just swap two vertices and leave everything else alone. Well, this is how I calculated it, but it's essentially 6 choose 2. We choose 2 of our 6 vertices to swap. Alright, we have, so what does that mean when we are thinking about which edges in our, so which colourings, which elements of A are fixed by the permutation 1, 2? We have, so when we swap this vertex 1 with this vertex 2, any edge from any other vertex to vertex 1 will sort of be mapped onto the edge from that vertex to vertex 2. So in this case that means that this edge and this edge, the ones coloured blue here, must be the same. So they must either both be there or not be there, so coloured black or coloured white. And similarly, these two edges from this other vertex must have the same colour. And where there's an edge I haven't drawn, so for example the edge between 1 and 2 or one of these other edges, it's free from constraint. We can colour it anything we want. So all we need to do now is count the number of choices we need to make. We started with 15 choices, so there are 15 edges in our complete graph. For each of those we need to choose whether to include it or not. But actually we are constrained here, so we can say, well, I'm going to choose whether to include this edge or not, but then I don't make another choice here, I just do exactly the same thing. I make a choice here but not a choice there, and so on. So actually I only have 4 fewer choices, so that's only 11 choices. So the actual number of colourings, the number of elements of A that are fixed by this permutation is 2 to the 11. Let's now go back to the identity permutation quickly. So there's nothing else that's like the identity permutation. We now have 15 choices with no constraints. So the number of elements of our set A that is fixed by the identity permutation is all of them, all 2 to the 15. So there are 2 more pages of these calculations. We have, for example, this, which switches vertices 1 and 2, then sends vertex 3 to vertex 4, sends vertex 4 to vertex 5 back to vertex 3, and it leaves vertex 6 the same. If you calculate how many permutations there are that act in the same way as that, or in other words are a combination, a product of a transposition and a 3 cycle, there are 120, and for this particular one, when we switch 1, 2, we again need, for example, these edges to be the same, but now we're also switching 3, 4 and 5 in a particular way, so that means that this edge to 3 needs to be the same as that edge to 4, needs to be the same as that edge to 5, but also this edge between 3 and 4 is going to move around, so every time it needs to be the same, and any edge between an element of 1 and 2 and an element of 3, 4 and 5, which is one of these orange ones, they all need to be the same. And we have a free choice for whether to include the edge between 1 and 2 or not. And if we check how many choices are we making in this case, well, we need to choose whether or not to include each of the blue edges, whether or not to include each of the orange edges, whether or not to include each of the green edges, and also the red edges, and also this final free choice between 1 and 2. So that's 5 choices. So we have 2 to the 5 colourings, 2 to the 5 elements of A that are fixed by each of these, or rather, each of these 120 permutations fixes 2 to the 5 of these elements of A. They may be different for each of those 120 permutations. And once we have calculated all of that, we just need to multiply these numbers together and sum across all of those rows. So we have that going on down here, and then we are also dividing by the number of elements in H, which is 6 factorial, 720. And we get 156, which is reassuringly an integer. And I believe that is the number of colorings of 6 vertices the number of subgraphs of this complete graph on 6 vertices up to rearranging the vertices. And in fact, when we have 2 subgraphs that are related by one of these permutations of the vertices, they are isomorphic. That's exactly what a graph isomorphism is. So the elements of one of our orbits are isomorphic subgraphs, and if 2 elements of A are in different orbits, they're not isomorphic. So in other words, the orbits are isomorphism classes. So 156 is the number of isomorphism classes of graphs on 6 vertices, which is a really nice application of our formula. Perhaps a better example to see when seeing this topic for the first time is the number of colorings of faces of a cube, where we are rotating the cube along any axis we like. And if you see lots of examples like that, then this application of the same formula to counting subgraphs is maybe quite surprising, but I just really like it. The fact that we're finding something as fundamental as isomorphism classes, isomorphism classes of graphs using, well, just by colouring some diagrams and applying this thing from group theory is surprising but really elegant. The title of this video is Burnside Lemma. You may think that the exciting formula we've come up with must be Burnside's lemma. In fact, it's not. There's a small generalisation. So we are now thinking about a finite group acting on a finite set. And in particular, that means we still have our finite set A, we still have the symmetry group of A. Now we're thinking about a group and a group homomorphism into our permutation group here. It's not really very different. It just means you can have 2 elements of G that sort of correspond to the same permutation, which couldn't happen in our previous setup. So again, we can write fix of G to be the number of fixed points, and then we have a formula which looks exactly the same for the number of orbits under this group action. We can prove this in, I think, two different ways. So either we can identify the subset, the subgroup H, which corresponds to this group action phi, and then we've already proved a formula for H, and then we can modify it to get our formula involving G. Or I think I would prefer if we just went back and rewrote everything in terms of phi and G. We still have labels, we could still draw some rings. The proof would work exactly the same, basically. And that result is Burnside's lemma. If you would like to fill in some of the details at the beginning, so in particular, why is it the case that inside an orbit the elements of our subset H, our subgroup H, or in fact our group G, are split into groups of equal size, into subsets of equal size, based on where the permutation is sending a particular element of our orbit. We used that fact, but we didn't prove it. That is a consequence of something called the orbit stabilizer theorem, which is usually written in this more general language of group actions. It's also worth looking up other interesting applications of Burnside's lemma. I'm sure you will easily find some exercises which are probably much easier than that second example I gave. And it may be worth learning about conjugacy classes. Which are essentially these things. So the conjugacy class of the permutation 1, 2 has size 15. So they are the 15 permutations that act in the same way as 1, 2, and it can be quite easily shown that all of the permutations in the same conjugacy class have the same number of fixed points. So that means we can confidently just pick one representative of each conjugacy class and calculate the number of fixed points, and then calculate the size of the conjugacy class. That gets especially helpful when the group G is more complicated than Sn or S6, because then the conjugacy classes are a little less intuitive. It may be the case that permutations like this, which seem to be doing the same thing, are not actually conjugate in a different group, and that is a warning that you do need to consider those cases separately. They may have a different number of fixed points in each case. Alright, that's quite a lot of stuff that may make no sense based just on what we've seen in this video. Hopefully it is clear that this formula we found is useful, and you have some sense of why it's true. Thank you very much.